So today I'm not going to. So finally we did the two coding, that regression and from Keras we have done the coding. Now we will check it out classification problems. So before that we have to find out some partial derivative equations because they are having little bit changes from the previous ones, right? As formula is the same, W1 is equal to W minus del L over del W. It also included. So that old weight is equal to new weight minus eta del L over del W. Alright, the figure is same, XIL, XI2. Yeah, I also did the little bit changes in the data set. We'll see further. So B11, B12 by SS, then B21, then we will get Y hat. So what is our loss function here? We are using loss is equal to binary in cross entropy, alright? So the question arises here why we are using binary cross entropy and log loss, alright? So it is referred to the same concept we have used interchangeably. They are all loss functions specifically tailored for binary classification problem. As we have two classes often refer to the positive class 1 and negative class 0. Binary cross entropy or log loss measures the dissimilarity between the actual labels and the predicted probabilities of the data points being the positive class. It penalizes the prediction that are confident but wrong. As you can see, mathematically, we have written the log loss function here. That loss is equal to minus y log y hat minus 1 minus y log 1 minus 1 y hat. Alright, so where y is the actual label and y hat is the predicted probability for the data point being in the positive class. So in short, binary cross entropy and log loss are two names for the same concept, and they play a crucial role in training models for binary classification by measuring how well the model's predictive probabilities align with the true level. So the question is why they are crucial for model monitoring. Monitoring these metrics can reveal how well our model's predictions are aligning with the actual outcomes, which is vital for evaluating its performance over time. They help in understanding whether the model is improving, staying constant, or degrading, which is especially critical in changing environments. Actually, understanding binary cross entropy, information theory basics, it is basis on information theory as entropy is used to measure the uncertainty or randomness of set of outcomes. This uncertainty is inherent in the data, and higher entropy means higher unpredictability in the data, right? So in the context of machine learning, lower entropy means that model's prediction are more reliable, while higher entropy implies more confusion, right? So if we look at the partial derivative equations, del L over del y hat is equal to del over del y hat. Inside the square bracket, we have loss function. Already you can see it clearly. That minus log y hat minus 1 minus y, then log 1 minus y hat. So if we did the partial derivative equation with respect to y hat, what thing we have find out? So we will focus on the y hat. So where y hat is present. So here from the first minus y log y hat partial, if we do the partial derivatives, will take, then it will come 1 upon y hat. Alright. Then minus will become minus minus 1 plus then 1 minus y hat. Actually minus, how it will come via doing that partial derivative equation. Some minus also came here, so it will become plus. So minus 1 minus y upon 1 minus y hat. And finally we have got del L over del y hat is equal to minus of y minus y hat over 1 minus y hat. Right? You can see. Then we get the del L over del z is equal to minus of y minus y hat. Alright, so here also we have used the activation function as sigmoid. So in above regression problem, our activation function of all three nodes are linear. Since it's classification example, so I have chosen sigmoid. Alright, so because of sigmoid, little bit changes will definitely arise. Also loss function binary cross entropy here. And when forward propagation takes place, just focus if you provide input like weight 0.1, then how we calculate the output, that we will see further. All right. So just because sigmoid to changes arises, first we have to find out the z of the sigma z, we will find out. Then loss function also some changes will also arise here. So activation sigma z, that is question mark, we have to find out. Then del L over del W211 we have find out. Del all three equations, there are two parameter are same, right? Del L over del W211 is equal to del L over del y hat multiplied by del y hat over del z multiplied by del z over del W211. Similarly, in all those, del L over del y hat and del y hat over del z. These two parameters are similar. So we have to find out 2 and 3. Total 5 parameters we have to find out here. Del z over del W211. In the second, del z over del W221. In the third, del z over del B21. So if we see L depends upon y hat depends upon zf, and zf depends upon O11. O11 is depends upon Z previous, and the Z previous depend upon W111. So how the equation will come out in the picture? Del L over del W111. Then del L is equal to del L over del Y hat. Means if we see the dependencies, just listen carefully. We see L is dependent on Y hat. So the equation became del L over del Y hat. Then del y hat is dependent upon zf. Then equation became multiplied by del y hat over del zf. Since zf is dependent upon O11, del zf over del O11. Then O11 is dependent upon z prev. Then del O11 over del z prev. Then z prev is dependent upon del W111. So del z prev over del 1 W111. So how it So finally we have find out all 9 derivatives here. We just recall it, then we will focus on the coding part. The equation was saying that we have imported NumPy and Pandas libraries for importing the dataset, and we did the little bit changes in the dataset also, that in the form salary in the form of 0 or 1. Alright, means 1 is for selection, 0 is for not selection. We have done. So we will see those things, but before that we will just recall the partial derivative equations. So first one was del z over del W211 is equal to minus y minus y hat multiplied by O11. Second equation is del z over del W221 is equal to minus y minus y hat O12. Then third bias equation is del z over del B21 is equal to minus y minus y hat. Alright. Then second one, how it forms, as if we recall, ZF is equal to W211 O11 plus W221 O12 plus B12. If we do the partial derivative, we will take the partial derivative with respect to O11. Then we'll check it out where O11 is present, and rest will become 0. So what resultant we get? Del ZF over del O11 is equal to W211. Similarly here O11 equation sigma Z prime, right, and del O11 over del Z prime is equal to O12 1 minus O11, and then ZP is equal to W111 XI1 plus W121 XI2 plus B11. So if we do the partial derivative, we will take with respect to W111, then we will find out only XI1. Alright. So the second partial derivative equation is del L over del W111 is equal to minus y minus y hat W211 O11. So 1 minus O11 XI1. So next equation is del L over del W121 is equal to minus y minus y hat multiplied by W211 multiplied by O11 multiplied by 1 minus O11 then multiplied by xi2. Similarly for bias, del L over del B11 is equal to minus y minus y hat W211 multiplied by O11 multiplied by 1 minus O11. Then our last derivative is last three. So if we look at the classification update parameter, then we will do the same thing, that we will find out the x and y and put those values on the updated parameters that we have find out. That for first df team grade dot value 0 dot reshape to 1 and y is equal to df place dot value 0 0. Then we initialize our parameter 2 to 1 as we have two biases, two inputs, and 2 to 1 we have find out. Then y hat a1 is equal to a layer forward x parameters, then y hat is equal to y hat 0 0. Then update parameters y hat a1 x. Then we'll print out, and what we print out, that is loss for our first team. That will be minus y multiplied by np dot log y hat minus y. Inside it minus y, then np dot log 1 minus y hat. That is our loss log function. So it is a little bit different, so that's why I am recalling those things. So we will change in the next slide dot values from 0 to 1. We will change the team 0 1 0 to 1, then 1 2 3 4 5. As we have total 6 teams, so we will do those things. All right, and we'll find out the parameters, updated parameters. Then we will go on the first loop. We will exit from the second loop and we'll go to the first loop. We'll find out the epochs implementation. All right, so finally we have find out the epochs of classification also. As first law, in I think in 6 laws we have find out 0.830. It is very less. I think classification is better algorithm, I think. I mean, as per our coding part we are seeing it. So in Keras we can say, and also in regression problem what weights we have, we can check it out. We can say it properly that from classification we have 0.10, 0.10 weight, 0.10 I think approx near about. Then bias says it is 3.5 multiplied by 10 to the power 6, very less. All right, very less. So in the form of 10 to the power 6. So in the Keras, if we cross check it, you can see that also in Keras we have weights 0.0 to 0, 1.0, 0.76, 0.96. Yeah, it is better. I think everywhere not more changes, more diversion is not here. Just little bit changes are present here. So yeah. So finally we did the Python coding via classification, via using Keras, and via regression. So what is the conclusion of doing all those things? I think conclusion is it is the best algorithm I can say. As if we go forward and we are not reaching to our target value, then we will go back and update our weights and biases. Little bit means some consequences until we reach our target. Then we will iterate those processes, so we will reach out the target value. This is the main aim by using gradient descent function. So what is the limitation of the backpropagation? Actually this question was arising in my mind, so I just want to know. So training data, the performance of backpropagation is dependent on the quality of the training data. Noisy data can affect the results of the backpropagation. Time is very important, so backpropagation models can take longer time to train. Or computational resources, it requires a significant amount of computational resources, especially for deep networks. On local minima, the network may get stuck in local minima, which can hinder optimal learning. As we were saying now, certain changes are occur in our first regression problem. Sometimes what happened, like in some point that is near about, so it is stuck there and it on that point and not going forward. So that's the problem, overfitting and underfitting. Backpropagation, as we have lots of training data, so then definitely those problems will arise. A spatial relationship that doesn't consider the spatial associative and disassociative relationship between classes when calculating errors. So activation functions, also backpropagation requires differential activation functions, which limits the choice of function used in the network. And initial voice setup, that is very important. So we have to look at carefully. Those setups can significantly impact the effectiveness of learning. And the biggest disadvantages of backpropagation could be rather sensitive to noisy data and irregularities. Performance of backpropagation relies very heavily on the training data, and it needs very large amount of time for training. And what is the advantage? Actually, it is very advantageous where we find higher accuracy. Like if we call it from medical field, we can say we need higher accuracy in the testing reports of like cancer, brain tumor, breast cancer, or anything like any disease. If we want higher accuracy, then we will go for the backpropagation. In the fraud detection, in the spam filter, and means the other where we need higher accuracy, then we will go with the backpropagation algorithm. So that is very, for supervised learning, it is very significant and very useful, we can say very advantageous. Also in unsupervised it is working, but not having much idea regarding this, so I'll find it out and tell you for those things. And what applications, I think I have told you, but we'll check it out more application and we see. Actually now backpropagation having huge application, computer vision, speech recognition, natural language processing, robotics, medical diagnosis, autonomous vehicles. As we are seeing, we are getting the autonomous cars. So backpropagation can use to train AI systems in autonomous vehicles to recognize objects, pedestrians, and other vehicles on the road. So for learning from the environment, it is highly recommendable. For natural language processing, can used, and for computer vision, it can be used to train the artificial neural networks to recognize the objects in images such as cars, people, or cats. In the computer vision, also face recognition. For those reasons, backpropagation is, I think, very well algorithm. So backpropagation is a gradient estimation method that uses the chain rule to compute the gradient of loss function. It works by computing the gradient one layer at a time, iterating backward from the last layer. So it is widely used and powerful technique in the field of artificial neural networks, and having a huge applications. If you go through the Google and search it out, I've told you little bit, just a little part of those things. It is huge. So finally today we have finished our backpropagation via theoretically or also via coding part. Okay? All right.